Hello dear friends, welcome to the lecture of ordinary differential equations. We are studying differential equations of first order and first degree. In this lecture we shall study exact differential equations. So what is the meaning or definition of exact differential equations? Some simple examples to understand it, and then we will state and prove the necessary and sufficient condition for exact differential equations. A differential equation which is formed from its primitive means integral or solution, from its solution directly by differentiation and without any further operation of elimination or reduction is said to be exact differential equation. That means the differential equation is formed or obtained by integrating its general solution, not integrating but differentiating its general solution. That is formation of differential equation. For example, if I consider examples of this one, the differential equation, say dx, we shall consider the simple equation dx plus dy is equal to 0 is exact. So why it is exact? Because it is obtained by differentiating the relation x plus y. It is obtained by differentiating some function of x and y. Differentiating, if I consider u is equal to x plus y, differentiating this function. That is, the derivative of this d of u du is d of x plus y, which is dx plus dy, and this function we should consider as c, and therefore c is a constant, and thus its derivative of c will be 0. So this is the equation that we have obtained by differentiating x plus y is equal to c, and therefore this differential equation is exact. So d of x plus y is equal to dx plus dy, and the right side is a constant, therefore its derivative is 0. So therefore this is exact differential equation, example of. Now the second can be considered as the differential equation, say y dx plus x dy is equal to 0. This is also exact. So why it is exact? Because it is obtained by differentiating on differentiation or differentiating the relation that may be considered as u is equal to, say, xy is equal to constant. This function, so some function of x and y that we are considering u, or simply you can say it is obtained on differentiating xy is equal to c. Now what is the derivative of xy? Derivative of d of total differential. You must note that this differentiation is total differentiation. It is function of x and y, and we have to consider the total differentiation. So what is the d of x and into y? That is from this. So that is, it will be du is equal to d of x y, and by product rule for differentiation it will be x into dy differential of y plus y into differential of x dx, and the right side is constant, so its derivative is 0. So thus there which is the same equation, y dx plus x dy is equal to 0. So therefore this is exact because it is differential of x y. So d of xy is equal to x dy plus y dx, and that is equal to 0. Therefore this becomes exact differential equation. So that is the meaning of exact differential equation. It is obtained by differentiating its primitive. Now what is the solution of this? Solution of this differential equation is xy is equal to c, and if you differentiate xy is equal to c, then we get the given original differential equation. which is exact. So that is the simple meaning. It is obtained by direct differentiation of its general solution, or which is also known as primitive or integral, and without any further operation of elimination or reduction. It is direct differentiation of the primitive, and that equation is known as exact. Now what is we will consider or see what is necessary and sufficient condition for the equation this type of. And again, one more thing we should note, the exact differential equation is of this type. So or this may be written as y dx plus x dy. First differential of x, then differential of y dx plus x dy. This is of the form m dx plus n into dy is equal to 0. What is m for this differential equation? M is y and n is x. And earlier equation we have written simple as dx plus dy is equal to 0. Dx plus dy is 0. This is also of the form m dx plus n dy is equal to 0. M is 1, n is 1. Or the equations of this type, x square dx plus y dy is equal to 0. This is also exact, and here m is x square and n is y. So that means a differential equation, exact differential equation can be written, or a differential equation of first order can be written in this form, m dx plus n dy. So this equation will be exact if and only if the necessary and sufficient condition means it is two-way. If this differential equation is exact, then partial derivative of m with respect to y is equal to partial derivative of n with respect to x. That is dou m by dou y is equal to dou n by dou x. Partial derivative meaning is we have to differentiate m partially with respect to y, means we have to treat x as constant, differentiate only with respect to y, treating x as constant. And when we differentiate n partially with respect to x, then y is to be treated as constant. That is the only difference in total derivative and partial derivative. So for example, if m is the function as x square y plus y square into x, then what will be its derivative with respect to y? When we differentiate this with respect to y, we treat x as a constant, and this x square becomes constant, and derivative of y is 1 with respect to y is 1. So it is x square plus here x is constant, so it remains the same, and derivative of y square is 2y. So it is 2xy. That is partial derivative of m with respect to y. And similarly, if you take the partial derivative of m with respect to x, then we have to treat y as constant. So here y is constant, it remains as it is, and derivative of x square we have to differentiate with respect to x, treating y as constant. We are differentiating with respect to one variable partial derivative, then the other variable is to be treated as constant. Here x is to be treated as constant. For this derivative, partial derivative, y is to be treated as constant, and y is constant, it remains same, derivative of x square is 2x. So it is 2xy and plus, and here this derivative with respect to x, treating y as constant, will be y square. So in this way we can get the partial derivatives of a given function with respect to x and y. Now that is here partial derivative of this function m with respect to y. It is with respect to y, that is also to be noted. It is a coefficient of dx, but it is differentiated partially with respect to y, and this n is differentiated partially with respect to x. Then if these two are equal, then the differential equation becomes exact, and then we will see also what will be the solution of this. First we shall consider the proof for the condition is necessary. The condition is necessary, and that means we shall assume this equation is exact, and then we shall prove this relation dou m by dou y is equal to dou n by dou x. Suppose m dx plus n dy is equal to 0. We will suppose this relation as 1 is exact, or that means is exact differential equation. Then what we have to prove is this one, dou m by dou y is equal to dou n by dou x. And because this is exact, there is a function u whose total differential is equal to this one. That's why we have considered du is equal to d of xy. So therefore there exists there is a function u of x and y such that this d of u is equal to m dx plus n dy. That is actually also can be considered as definition of exact differential equation. If there exists a function u such that total derivative of that u is equal to the given differential equation, then the given differential equation is said to be exact, and thus we have this relation. But what is the total differential? There is a theorem on total differential. If u is function of x and y, then the total differential is written in terms of partial derivatives. Partial derivative of u with respect to x into differential of x plus partial derivative of u with respect to y into differential of y. So this is the theorem in partial differentiation. Total derivative is total differential is expressed in this form in two parts. First, partial derivative of u with respect to x into dx plus partial derivative of u with respect to y into dy. Now comparing these two, comparing their coefficients on right side. So coefficient of dx is m here, and here it is dou u by dou x. So these must be equal, and here n also must be equal to this. So comparing coefficients, or these imply m is equal to dou u by dou x and n is equal to dou u by dou y. Now we will suppose this relation as second. Now from this second relation we want to eliminate u, and we want to get the relation between partial derivatives of m and n, and for that purpose we will differentiate first m with respect to y partially with respect to y, differentiate m partially with respect to y, and we differentiate n partially with respect to x. So that can be considered from the condition, given condition. So therefore dou m by dou y, partial derivative of m with respect to y, that is therefore dou m by dou y is equal to, differentiate this partially with respect to y both side, and that derivative symbol can be written as dou by dou y of right side is dou u by dou x, or which is dou square u by dou y dou x, and what is dou n by dou y, dou n by dou x. Differentiate this partially with respect to x, first with respect to y, second with respect to x, because we want to get this relation, or we actually want to prove these are equal. And dou n by dou x is dou by dou x of what is n, dou u by dou y, and that is dou square u by dou x dou y. Now we have the partial derivatives. These two partial derivatives are equal in general. Dou square u by dou y dou x is same as dou square u by dou x dou y. If these two are equal, then these two must be equal. So as dou square u by dou y dou x is equal to, second order partial derivative of u with respect to y and x are equal. This implies, or these implies, dou m by dou y is equal to dou n by dou x, and this is what we wanted to prove. These two are equal because their right sides are equal, and this is the condition, and thus the condition is obtained, hence the necessary condition. Hence the condition is necessary. That part we have proved. Assuming the equation is exact, we have proved these two partial derivatives are equal, and hence the condition is necessary. Now second part is the condition is sufficient. That is converse actually part. Suppose these partial derivatives are equal, then we have to prove the differential equation is exact. The condition is sufficient. For this, let or suppose dou m by dou y is equal to dou n by dou x. That means 3 holds. We shall prove, or we have to prove, m dx plus n dy is equal to 0 is exact. And when it is said to be exact, if there is a function u such that du is equal to this expression, we shall find u, a function u of x and y such that du is equal to m dx plus n dy. If we could find this function u like this, then the equation becomes exact. So by definition of exact differential equation. Now we shall what we shall further do is integrate this with respect to x, treating y as constant. So that is also a partial integration, integrating this with respect to x. Keeping y constant or fixed, keeping y fixed or constant. We get, so integration of du is u. So I shall write u on left side, integration of this, and I write the symbol of integration for this integral of m dx. So here we are integrating with respect to x only, and here y is to be considered as fixed or constant, and therefore this term will not contain x. The remaining terms will not contain x. That is term not in x or terms free from x plus terms free from x or terms which does not contain x, free from x, the meaning, or that is this will be u is equal to integral m dx plus, and these terms are free from x means these terms will contain only y or constant, and that will be a function of y. We write that function as f of y, and we will suppose this is our next equation, fourth equation. Now what we further do is differentiate this partially with respect to y. Differentiating for partially with respect to y. So what we shall get is partial derivative of this is dou u by dou y is equal to, and again partial derivative of this we shall write the symbol dou by dou y of integral m dx plus derivative of this partial derivative of f of y with respect to x, but f of y is a function of x y only, and therefore this is function of single variable, and when there is function of single derivative, the single variable, the derivative becomes total, or instead of writing partial derivative we write the total derivative d of fy divided by dy, d by dy of fy. So what is the difference in this? Because these are functions of see here two variable it may be, and here y may be existing there, and therefore we have differentiated this partially with respect to y, but this is function of single y variable, and therefore the derivative is written for this as total derivative d by dy. So this we have obtained. From this we shall express, but now you see what is the dou u by dou y. Dou u by dou y, we have the second relation here itself. Dou u by dou y is n. So this left side is n, but dou u by dou y is n. This is by 2 from second relation, and therefore the equation becomes, therefore we have n, left side is n is equal to, this is n is dou by dou y of integral m dx plus d of fy divided by dy, d by dy of f of y, capital F of y. From this we write the value of d by dy of capital Fy is equal to, so this will be n minus shifting this term on the left side, dou by dou y of integral m dx, and this we shall assume as equation number 5. Now we observe equation 5. The left side of equation 5 is not involving x, is independent of x, because this is entirely function of y. So this does not contain x. Similarly, the right side does not contain x, that we shall show by taking its partial derivative with respect to x. So this will be constant with respect to x, and that I shall write. So this is our third equation. We see, I may write here itself, this is our third equation, and this we have assumed as our first equation, and this is our second equation. So now I shall rub this. The LHS of 5 is does not contain x. The left hand side of 5 does not contain x, that is clear, because it is function of y and differentiated with respect to y, total derivative is with respect to y. The right side of 5 also does not contain x, and the reason for this is, for if you take the partial derivative of this right side with respect to x, for dou by dou x of n minus dou by dou y of integral m dx. So what will be this derivative, partial derivative? So this is actually partial derivative of n with respect to x minus, and what will be the partial derivative of this with respect to x? See, this operator remains as it is, and this is integration with respect to x, and this is the partial derivative with respect to x. So this is also partial integration. We have written integrating this with respect to x, keeping y fixed. This is the integration. And if you differentiate, the integration and differentiation are inverse, and therefore this partial derivative with respect to x cancels the integration with respect to x, and this m will remain as it is, and this becomes minus dou m by dou y. This derivative cancels this integration. Inverse process of operating derivative on the integration with respect to same variable x. This is derivative with respect to x, this is integration with respect to x, and the product of these will be cancelled, and then what remains is dou m by dou y. But you see, these two are equal. Dou n by dou x is equal to dou m by dou y because of 3. This we have assumed. Dou m by dou y is equal to dou n by dou x, and there, so equal quantity are subtracted, the subtraction is 0. And what is the meaning of this partial derivative is 0 with respect to x. The derivative with respect to x is 0, means the term is constant with respect to x, and therefore this term does not contain x because its derivative is 0, and thus we have these terms are independent of x. Now what we shall further do is integrate 5 on both sides with respect to y. Integrating 5 integrating both sides of 5 with respect to y, we get. Now see what we shall obtain on the left side. If we integrate this with respect to y, the derivative and integration are inverse of each other and the effect cancels, only f of y remains, and we get f of y, capital F of y is equal to, and this is to be integrated with respect to right side is also to be integrated with respect to y, but here we shall keep the same expression in bracket and integrate this with respect to y, that is integral n minus dou by dou y of integral m dx into dy. So this is the right side. The left side is only f of y, and the right side integral of the right side with respect to y. So this value of f of y we have obtained. Now we shall put this value of f of y in equation number 4. So putting this in 4, we get or substituting this value, we get u is equal to integral m dx plus f of y. And one more thing we should have to consider here is we have integrated both sides, and we shall add a constant of integration as a. When we integrate, we add the constant of integration, and the constant of integration is written as a, where a is constant of integration. And now this value is substituted here, so that means this is f of y, integral n minus dou by dou y of integral m dx into dy plus a. So thus this is the function that we wanted to obtain, u has this value, and such that the equation becomes d of u will be m dx plus n dy. So this is the function u for which du is equal to m dx plus n dy is equal to 0. This is actually this will be the solution of 1. This is the function which is the solution of 1, or which is the general solution of 1. This is the function which gives the general solution of 1. That is, u is equal to a constant. Another constant is the solution of 1. And thus 1 is exact. Hence 1 means this differential equation is exact, and this proves the condition is sufficient, and this proves the theorem. Thus we have proved that the necessary and sufficient condition for this first order differential equation m dx plus n dy to be exact is dou m by dou y is equal to dou n by dou x. And now we will write a working rule for solving exact differential equation. So working rule is to be written with the help of this theorem. Actually, this u is the solution. Working rule for solving exact differential equation. Now let m dx plus n dy be given equation. Be the given equation or given differential equation. Then check dou m by dou y is equal to dou n by dou x. That is the condition necessary. First check that condition. If this satisfies, then we may suppose this as 6, equation 6. Then from equation 6, the solution is u is equal to constant. But what is u? See, u is integral m dx, and we should note that integral in this integral of m dx, we have treated y as constant, and this is the term of n which are free from x. We have proved this in the equation number 5. This term is free from x, means this term does not contain x. And how we have proved this? Taking with the partial derivative of this with respect to x, and that is 0. Therefore this is independent of x, and that means n minus this term is the terms of n which are not containing x. That is the meaning of this part. So there are two parts in the solution, and the solution I shall write here as this is integral m dx, say, or I shall write with the same pen, that will be integral m dx. Here y is constant, plus integral terms of n not containing x. This is differentiated with respect to y, and the right side is constant. U is equal to C. So this is a constant and this is a constant. So total constant is written as C only. A is shifted on that side. It will be C minus A, again a constant. And thus this is the working rule for exact differential equation. So this is to be remembered. So what we have to remember is the theorem. This theorem is also important for, that is the condition for the exact differential equation. Dou m by dou y is equal to dou n by dou x, or that is also written here. So the equation should be in this form. Then get the value of m and n, check this, and if this is satisfied, then this will give the general solution of the exact differential equation. The problems of exact differential equation we shall solve in the next lecture. Thank you.